法政大学の斉藤でございます。よろしくお願いします。Welcome to webinar, an introduction to multi-objective optimization programs in nonlinear circuits and systems. Contents, Introduction. Part 1, multi-objective optimization programs in continuous time systems. Boost converters with photovoltaic input PV input, stability versus efficiency, conclusions, and theme proposal 1. Part 2, MOPs in discrete time systems, dynamic binary neural networks, stability versus connection sparsity, conclusions, and theme proposal 2. Questions welcome, especially from young researchers. Via chat, please. We consider multi-objective optimization programs in nonlinear systems. For example, switching power converter and recurrent neural networks, characterized by parameter P. The problem requires simultaneous optimization of multiple objectives. For simplicity, we explain it in the bi-objective optimization programs, BOPs. Maximize two objectives, F1 and F2, a function of parameter. For example, F1 performance and F2 cost. In such programs, we often encounter trade-offs. If one objective becomes better, the other objective becomes worse. The trade-off is characterized by Pareto. So we explain the Pareto briefly. The Pareto characterizes trade-offs in this BOPs, minimize two objectives. Here, domination relationship is important. In this figure, this green point, F of P1 dominates F of P2. If these conditions are satisfied, in this condition, both first and second objectives are better. F1 is better, FP1 is better. And here, the second objective is the same, but first objective is better. Here, the first objective is the same, but second objective is better. Here, please note that these green 3 points are not dominated by any other point. The Pareto front is a set of non-dominated points. In this case, these 3 points, F of P4, P1, P3, are Pareto front. And there exists a variety of interesting evolutionary algorithms. But they are applied mainly in benchmarks. The application in nonlinear CAS is not sufficient. Then we consider BOPs in nonlinear CAS. There are two categories, continuous time system and discrete time system. The continuous time system is described by ODEs, and it exhibits various nonlinear phenomena, multiple equilibrium points, periodic orbit, chaos, and bifurcation. The applications include switching converter, reservoir computing, and so on. In discrete time system, dynamics is described by difference equation, and it exhibits various phenomena. Even in simple one-dimensional system, the system exhibits very complicated dynamics. Then we explain the famous example, the logistic map, published in Nature 76. This very simple unimodal curve gives nonlinearity. The dynamics is described by this reference equation. Xn is a state variable at discrete time n, and it has only one parameter, A. In this case, this map exhibits chaotic behavior. This simple deterministic system exhibits very complicated dynamics. This is very famous period doubling bifurcation. Here, as peak is low, here exists stable fixed point. This plot here. The parameter A here and the steady state is plot here, the fixed point here. As A increases, the fixed point bifurcates to period 2 orbit this cycle, and then to chaos. This is period doubling bifurcation to chaos and very famous example. Even in this very simple difference equation, the system exhibit various nonlinear dynamics. Then the higher dimensional system exhibit a variety of nonlinear phenomena. A multiple fixed point, multiple periodic orbits, and chaos bifurcations. And applications include multiple fixed point to associative memories, and multiple periodic orbit to control signals of working robot. Then the MOP, multi-objective optimization problem. The objectives are defined in the applications. Then the BOP in nonlinear circuit and systems, characterized by parameter P. There are two cases. If it is required to maximize both two objectives, then the trade-off is characterized by this convex curve. This is Pareto form. And in minimized case, the Pareto is given by this concave curve. The Pareto front give the basic information to circuit design and analysis. Then we introduce part 1, MOPs in continuous time systems. The boost converter with photovoltaic PV input. In carbon neutral technology, renewable energy is very important. Solar power, wind power, and hydro power. And we consider solar power in this webinar. Then this is PV input, solar cell, and switching power converter convert the PV input and apply it to the load. The main technique is maximum power point tracking. That is, extracting the maximum power from the PV input. This figure, input voltage here and input current here. And the voltage current characteristic vary depending on external environment. It vary depending on irradiation, temperature, and so on. And the maximum power point, voltage versus peak, maximum power point moves depending on external environment. Very complicated, complex. And for simplicity, we consider static case. We fix this PV curve. Here we explain the switching power converter briefly. These are basic DC-DC switching power converters. And the boost converters are used in this webinar, but we introduce 3 basic DC-DC switching power converter. The boost converter, the input, if switch is on, input energy is stored into inductor. The switch off, the energy is applied to the load. The boost converters give higher voltage than the input. The buck converter gives lower voltage than the input. And the buck boost converter gives both larger and lower voltage than input. And there are mainly two kinds of control strategy, current mode control and voltage mode control. Anyway, there exists a variety of DC-DC switching power converters, but we focus on this case, boost converters in current mode control. And photovoltaic PV input is applied to this converter. Here, as a basic concept, we emphasize importance of the switch S. It goes without saying, power consumption in the switch is zero. That is, if switch is open, the current is zero. And if switch is on, then voltage is zero. Anyway, instantaneous power is zero. It is very convenient in energy efficiency. Here, we consider boost as a model, boost converters with PV input. And maximum power point tracking is a major technique. Usually, researchers consider single objective optimization problem. They consider to improve efficiency. But stability is also important. Then in bi-objective optimization program, we should consider to improve both stability and efficiency. Then we consider BOP boost converters with PV input. Maximize two objectives. First objective is stability, and second objective is efficiency. Detailed definition is given afterward. And palette front gives basic information to circuit design and analysis. However, there are bottlenecks that include the precise calculation of objectives, F1 and F2, is not easy. Anyway, the input characteristic is given by complex nonlinearity, and circuit include a complicated nonlinear operation. Then the precise calculation of objectives and palette front is not easy. Then we apply piecewise linear modeling for precise calculation of the objectives. First, we simplify this voltage current, input voltage current characteristic to two-segment piecewise linear function. Then we replace PV input with current-controlled voltage source. It is controlled by inductor current. And also, if time constant of the load is much larger than the clock period, this load can be simplified into constant voltage source. In this simplified system, size analysis is possible. And the result can give basic information to analyze various realistic systems, but analysis is, this system is very convenient. Then we explain dynamics. This is a circuit model, simplified circuit model. It includes switch S and diode D. We assume that the S and D is either state 1 or state 2. In state 1, switch on, diode off. And in state 2, switch off, diode on. And this figure is described by this piecewise linear function, characterized by 4 parameters, RA, RV, breakpoint VB, and IP. And in state 1, the dynamics is described by this differential equation, and in state 2, described by this equation. So next, we define switching rule. If present state is 2, it changes into state 1 if inductor current reaches lowest threshold I1. The threshold I1 is a key parameter in current mode control. And if present state is 2, it changed into state 2 if clock t arrives. And next, we simplify the ODE into dimensionless form. We define dimensionless variables and parameters, normalized time tau, normalized by time constant, and dimensionless current x, and dimensionless input voltage y. And alpha, beta are proportional to slopes, and TP is clock period, x minus, lowest threshold, and Q output. Using these dimensionless variables and parameters, the circuit equation is simplified into this one. State 1, this equation, state 2, this equation. Using in this equation, the major advantage is calculation using piecewise exact solutions. This is a piecewise linear equation. And in state 1, the dynamics is described by this equation, and we can calculate. We have the simple piecewise exact solutions like this. And state 2, we also have piecewise exact solution like this, where A1 to B2 are given by parameters. The connecting these solutions, precise exact analysis is possible. Using this piecewise exact solution, we can analyze dynamics. So this converter is nonlinear dynamical system and can exhibit a variety of nonlinear phenomena. We show some examples. The first, this is period 1, very simple periodic orbit. This is a dimensionless current, the dimensionless instantaneous power, and this is return map derived from this system, present state and next state. And this fixed point, stable fixed point, corresponds to this period 1 wave. As parameter varies, we obtain period 2 orbit, this cycle, and chaos. And we can analyze chaotic behavior theoretically. And chaotic behavior may be applicable to EMC. But in this webinar, for simplicity, we focus on this case. Anyway, the system exhibits a variety of nonlinear dynamics, but we consider, we focus on period 1 orbit in this webinar. Then we consider BOP, bi-objective optimization problems. We define first objective that characterizes stability of period TP, period 1 orbit. This is a period 1 orbit, and delta x0 is initial deviation, and delta x1 is next deviation. And this term express contraction of the orbit. And subtracting from 1, we obtain the first objective. The super stable case, x1 is 0, then that case, fp1 is 1. That is a super stable case. Anyway, as f1 increases, stability becomes stronger, approaches to superstability, and the transient phenomena becomes faster. Using exact piecewise solution, we obtain theoretical formula of this first objective. The second objective characterizes input energy, average input power. This is a dimensionless current and a dimensionless instantaneous power. And averaging this, we obtain average power. As F2 increases, extracting input power becomes larger. It is basic to in the maximum power point tracking technique. Then, using exact piecewise solutions, we obtain theoretical formula. Also, the dimensionless equation is characterized by 5 parameters. Analysis in 5-parameter space is not easy because of dimensionality. Then we focus on only one parameter for simplicity, Q. That relates to output voltage or output load. And other 4 parameters are fixed after trial and errors. In this case, 2 objectives are described by a function of parameter Q. Using exact piecewise solution, we have calculated the period 1 waveform. And in this case, Q is 1.28. Stability is not so strong, but efficiency is high efficiency. And in this case, stability is strong, but efficiency is not so high. These basic calculations suggest existence of trade-off between 2 objectives. Then we consider this trade-off, BOP, in more detail. Here we define bio-objective optimization problem that maximize F1 and F2. F1, stability, F2, average input power, efficiency. And the parameters, Q varies and other parameters are fixed. Then we try to find Pareto. But we have theoretical formula, then we can calculate Pareto exactly. We omit detailed calculation, but we show the result. This is a Pareto, the objective space. First objective here, the second objective here. And this blue curve is a Pareto, given based on the definition of the Pareto, non-dominated point. This result is exact and precise. We obtain this result by applying the brute force attack to theoretical formula of the objectives. Here, in point A, we obtain this waveform. Here, stability is not so strong, but efficiency is high. And this point, we obtain this waveform. Stability is strong, but efficiency is low. Let us consider this Pareto. It gives important information to circuit design, the parameter setting. If we have priority to efficiency, we select parameter here. And we have priority to stability, we should select this point. However, please note that in this point, both stability and efficiency is the best. But please note that the best efficiency and the best stability is impossible in this circuit. This is a basic information, very important information to circuit design. The Pareto is important. Anyway, the best efficiency and the best stability is impossible, and they exist trade-off. It is clarified theoretically, precisely using piecewise linear model. Here we conclude the part one. We have considered bio-objective optimization problems in boost converters with PV input. The first objective evaluates stability, and the second objective evaluates efficiency. The applying piecewise linear modeling, the objectives and the Pareto were calculated exactly. The Pareto guarantees trade-off between 2 objectives. And this is important information to circuit design, efficiency or priority, stability priority, and so on. Here, we propose theme 1 for future study. That is multi-objective optimization problems in dynamic PV input. Now we have considered the case of fixed PV characteristic. But in actual environment, the voltage current characteristic vary depending on external environment, irradiation, temperature. For example, partial shading condition, it moves. Maximum power point is also moves. Anyway, the characteristic is time variant. In that case, if we consider the bioobjective programs or multi-objective programs, the palette front is not fixed. It's time variant. Then the calculating dynamic palette front and considering the parameter design, it seems to be important research theme in the future. This is my proposal as same proposal one. Part two, MOPs in discrete time systems. Dynamic binary neural networks, a simple recurrent neural network. Let us begin with introducing classic simple discrete time recurrent neural networks, consisting of simple neuron. The N input is applied to a neuron, characterized by smooth activation function. Weighted sum is applied. And for simplicity, we set threshold 0. If the input exceeds threshold, excitation. Below the threshold, inhibition. Then connecting these neurons and applying delayed feedback, we obtain dynamical system described by this difference equation, where x sub j(t) real valued state variable at discrete time t, and wij is connection parameters. This is vector form. Usually, threshold parameter, it has threshold parameter, but we omit it for simplicity. Then this is very high-dimensional nonlinear system. It exhibits nonlinear phenomena. As stated earlier, the very simple difference equation exhibit very complicated dynamics. Then this dynamical system can exhibit a variety of complex nonlinear phenomena, the multiple variety of multiple fixed point and periodic orbit, chaos, hyperchaos, and bifurcation. And applications include associative memories, control signal of nonlinear circuit and systems, for example, robot, switching power converter, and time series approximations. Considering these many applications is not easy, then we focus on the associative memory in this webinar. This is a vector form. X is a vector of n-dimensional real-valued vector. Then we consider BOP in recurrent neural networks, characterized by parameter. Usually, this is a connection matrix of connection parameters. And we consider BOP. Here, not maximize, but minimize two objectives, F1 and F2. For example, F1 stability and F2 sparsity. This is objective space and the palette front. Then in this case, palette front can give basic information to analysis and synthesis. And please note that the synthesis is related deeply to multi-objective learning. Usually, machine learning is based on one objective, one cost function. But learning based on more than two objective functions seems to be very important. Then the MOPs have been studied mainly in the function type neural networks, multi-layer perceptron, convolution neural networks, and so on. However, MOPs in recurrent neural networks study is insufficient. The reasons include the RNN is very complicated nonlinear dynamic systems exhibit complex nonlinear dynamics. Anyway, RNN are hard to consider MOPs, then we use a simplified system. The dynamic binary neural networks, DBNN, or precise analysis of the BOP. This network is our original system. Here, the differentiation is similar, but activation function is binary. In this case, the state variables is binary. Here, x is a binary state variable at discrete time t. And also, the connection parameters are ternary. This is the diagram. The present state variables, binary state variables here, the next state variable here, activation function, and plus connection. Red is plus connection, positive connection. The blue is negative connection. And 0 means no connection. The vector form, they're characterized by connection parameter W. And X is n-dimensional binary vector. And W is connection matrix. The DBNN is suitable for precise analysis of nonlinear dynamics and FPGA-based implementation for engineering applications. FPGA, roughly speaking, FPGA is reconfigurable digital circuit. Okay? DBNN, characterized by connection parameter T, and described by difference equation of n-dimensional binary vectors and the connection parameters W. Since the number of n-dimensional binary vectors is finite, the steady state must be periodic orbit, including fixed point. Here, steady state is a multiple fixed point. In this figure, S1, S2, S3 are binary vectors. They are fixed point. S is transformed into itself by this function, fixed point. And the green circle represent initial point falling into a fixed point. The initial point is used to define stability of fixed point. The application of this fixed point include associative memories. This binary periodic orbit. F1 is transformed into F2 and F2 to S3 and return to itself. This is period 3 binary periodic orbit. And green point are also initial point. It is used to define stability. And applications include control signal of working robot, time series approximation, and so on. In this webinar, we consider this simple case, the steady state of fixed point and application associative memories. But in same proposal 2, we introduce binary periodic orbit and control signal application to control signal, controlling working robot. The associative memory. This is a fixed point and initial point. For example, if initial point is red, this is input. And if it fall into S1, this is apple, then we associate apple. This is a brief explanation of associative memory. Then formally, the desired memories, in this case, apple or banana or piman, something like that, represented by M binary vectors, S1 to Sm. And we consider simple case, the symmetric case, then we also consider inverse vectors, but we omit these for simplicity. And the storage of desired memory means we can set parameters such that the desired memory is a fixed point of this difference equation. Anyway, desired memories are n-dimensional binary vectors, and the storage of desired memory means fixed point of DBNN. Then we have storage condition. This is very classic result published in 94, but if parameters, connection parameters satisfy some condition, storage of all desired memories is guaranteed theoretically. This is basic to consider associative memory in DBNN. Then there exists a variety of parameter setting methods, but we use the most basic one. That is based on correlation learning. Again, M binary vectors are desired memories, binary vectors, and we apply Hebbian learning to obtain Cij, and binarying them, we obtain cross-correction parameters. And based on the storage condition, we determine self-feedback parameters. If we set these parameters, all the desired memories are stored. Anyway, Hebbian learning, binarization. In this case, the connection matrix is full binary. This is an example. If we prepare these four desired memories, 8-dimensional binary vectors, and applying the parameter setting method, we obtain this 8-dimensional connection matrix, full binary. In this case, memory stability is evaluated by the number of initial points. 108 initial point of 256 fall into desired memories. Here, we define BOP, Bio-Objective Optimization Problem. The first objective characterizes memory stability, defined based on the initial points falling into desired memories, normalized by all initial point and subtracting from one, we obtain first objective. As first objective decreases, memory stability becomes stronger. It is the inverse case of the part one. But in this case, decreasing stability is stronger. In this example, 3 initial points fall into first fixed point, 2 to second fixed point, 2 to the third fixed point. Then the first objective is calculated like this. And the second objective characterizes connection sparsity. That is characterized by zeros in connection parameters. Normalized it and subtracting from one, we obtain second objective as parameter of cross connection, as function of cross connection parameters. As F2 decreases, connection sparsity increases. It corresponds to lower power consumption if the DBNN is implemented in hardware. In this example, the no sparse connection, no zero connection, then the F2 is 1, the bad case. And here, 36 wires are open, then the F2 is given by this. Using these two objectives, we define bio-objective optimization problems, BOP. So minimize both F1, memory stability, and F2, connection sparsity. Then we try to find a trade-off, Pareto plot, that is, in the objective space, F1 and F2. Here we reconfirm Pareto plot. The definition is inverse than the previous one, in part one. The BOP is minimize two objectives. And if W1 is dominate, if W2, if these conditions is satisfied, if W2 is in this region, the both F1 and F2 is larger, or either F1 or F2 is larger, then F1 dominates F2. And the palette front is set of non-dominated points. These three red points are palette front. Then we have performed basic numerical experiment, minimize two objectives, and we use very simple example for desired memories. And applying fixed correlation-based learning, we obtain initial individual, the full binary connection matrix. The applying simple evolutionary algorithm outline is explained afterward. We obtain palette front. In the algorithm, specification is used as mutation, inserting zero element into the cross connection matrix, cross connection parameters. This is the result. The first full binary connection is plotted here. The 108 initial point falls into DMs. The stability is median, and the sparsity is no sparsity. As the sparsity increases, we obtain this point. The number of zero element is 12. In this case, 196 initial point fall into that memories. Stability becomes stronger. Stability becomes stronger. Here, the 36 zeros are inserted. Then 124 initial points fall into DMs. Stability weak. Sparsity increases. And here, number of zero element is 50. The stability becomes weak. In this palette front, we can confirm trade-off between stability and sparsity. Here we explain outline of the algorithm, evolutionary algorithm. If a dimension of DBNN or parameter space is low, the brute force attack may be possible. However, if dimension becomes higher, the exact calculation is impossible. We must use some algorithm, for example, evolutionary algorithm. Then we have used simple algorithm based on MOEAD. This is a very famous multi-objective optimization algorithm presented in this paper. That is, we explained briefly. First, the BOP is decomposed into scalar subproblems. There are various ways to construct subproblem, but we explain the weighted sum problem, characterized by parameter lambda k, and L subproblems. Okay, decomposed into subproblems. And this is algorithm outline. At first generation, we prepare initial individual. In the last example, full binary connection. And step 2, generate offspring. The applying mutation, inserting 0 into connection matrix, and evaluation by this function. And step 3, we calculate palette front candidate at generation G. And the palette front candidates are stored into external population, EP. And we repeat this procedure until maximum generation limit. At this maximum generation limit, the external population gives approximated palette front. Very simple outline, but this MOEAD or some evolutionary algorithm is very effective to calculate palette front. So we briefly show the evolution process in the algorithm. We prepare hundreds of sub-problems decomposed into hundreds of problems. And the maximum generation is 56. It is given after trial and errors. That initial generation, the full binary connection is plotted here. This objective space F1 and F2. This is generation and number of Pareto root candidate, number of element of external population. First here, and next 20, about 10 Pareto root candidate here, and 30 increases of spring and Pareto root candidate at generation 30, and last generation, we obtain Pareto root, approximated Pareto root. Then here we conclude part 2. We have considered BOP in DBNN, a simplified discrete time neural networks, recurrent neural networks, characterized by signal activation function and ternary connection parameters. And we consider case where the system has multiple fixed points corresponding to desired memories. Storage of desired memories is guaranteed. And in BOP, the first program, first objective memory stability, second connection sparsity. The first sparsity increases, the stability becomes stronger. And after that, there exists trade-off between sparsity and stability. Here, we propose same proposal 2. That is MOPs in DBNN with multiple periodic orbit, not fixed point, but periodic orbit. As stated earlier, the DBNN has multiple fixed point. This is one example, period 3 orbit of binary vector. Then this is just a prospect. If first objective is stability and the second objective is period and obtain this Pareto root. Here, period long, but stability weak. This case is applicable to time series approximation. It requires a long period. And here, period is short, is not long, but stability is strong. It is suitable in application to control walking robot. Anyway, this Pareto front gives important information to application of BOP. This is just a prospect. We briefly explain the application to walking robot. This is a BPO, binary periodic orbit, measured in FPGA board, simple experiment. The BPO1, period 6, the period 2. And this is 6-dimensional binary vector, periodic orbit of binary vectors. And the 6 bits corresponds to 6 legs of the walking robot. Then the periodic orbit corresponding to walking pattern. Here, first walking pattern is switched into second one and return to first one. If BPO is very stable, stability is strong, the switching is guaranteed. Then the strong stability is convenient in application to control signal. Switching of working patterns. This is one example. Anyway, we propose MOPs in multiple binary periodic orbit. And in the first part, we have proposed MOPs in dynamic PV input and a dynamic Pareto front. Now, this is the end of my webinar. Please give me the question by chat if possible. Some question, a comment? I wait 1 minute for question, but no question. I give short comment and conclude the webinar. Okay, maybe no question, but we hope that we have proposed 2 new study direction. Then I hope this proposal trigger to studies of some researchers. Thank you very much. Now we conclude the webinar. Thank you very much.